Firstly, the introduction of this chapter, structure of atom. Okay. So, to begin with, today I believe it is a bright sunny day. Okay. So, to begin with, let's have a look at this picture on your screen. Atomic structure. This is a diagram which I have been seeing since class 8, 9, and 10. In the center there is the nucleus, and around the nucleus there are orbits, orbitals, or shells containing electrons. If you look at this cartoon impression over here, there are four boxes. If you look at the first box, you can read carefully. I hope you can read. I hope you can read. Hey, miss, what do you why did you mark me wrong on question number 4? That is the first impression over there. After that, draw the parts of an atom. So you left it blank. Okay. Then this fellow says, I do it to the actual size. Okay. That means an atom is very, very small. It is very, very small. It cannot be seen with the human naked eye. Okay. Now, here this chapter is one of the important chapter in chemistry. It's a very important chapter in chemistry with regard to electrons, protons, and what we call neutrons over here. And we'll be learning about so many other things also in this chapter with regard to the numericals. Moving to the next slide, if you see, if the question is asked, name the fundamental particles in an atom, please answer electron, proton, and neutron. Okay. Now, to just give you a brief overview of what I am trying to explain you today. Molecule, molecule, then inside the molecule you get atom. Inside the atom you will have the nucleus. In an atom, just outside the nucleus there are electrons in the shells, and inside the nucleus you will find the protons, okay, and the neutrons. If you still move further, then you can get quarks. Okay. So this is just a brief overview of the fundamental particles in an atom. Now, if you look at the characteristics of the subatomic particles, you can have a look over here. Neutron symbol is N naught. Proton is P plus, electron is E minus. The location of the neutron, what you call neutron, is nucleus. Proton is also nucleus. And electrons you will find in the cloud, in the energy levels. The masses. The mass of a neutron is 1 atomic mass unit. Proton is 1 AMU again. Electron, it is negligible. Charges, 0 charge neutral. Plus 1 is proton and minus 1 is electron. So this is how to begin with the chapter. Now moving further, the first thing that we are going to learn slightly in detail is regarding the discovery of electrons, which are also called cathode rays. And this experiment was carried out by Sir J.J. Thomson, where there is a discharge tube, and this discharge tube is connected to a vacuum pump, to evacuate, bring down the pressure, to lower the pressure. And there are electrodes. The anode is there connected to the positive terminal of the battery. The cathode is there connected to the negative terminal of the battery. Okay, and then when around 10,000 volts of potential difference was applied across the ends of the cathode and anode, then some particles were emitted from the cathode which started to move in the direction of the anode. After hitting the anode, it was observed by Sir J.J. Thomson that there was a green glow behind the anode. Okay, so that was about how the discovery of electrons, the cathode rays, took place. This was the experimental setup done at that time. Okay. Now, going further to the details of these characteristics of cathode rays or the electrons, the cathode rays travel at straight line. They travel in straight line in vacuum, empty space. Cathode rays, they have energy and momentum. They produce fluorescent effect on fluorescent screen. They carry negative charge. They are negatively charged. That's why they deflect towards the positive terminal in the electric field. They also deflect in a magnetic field. Deflection direction is determined by Fleming's left-hand rule, which you have learned in class 10 in physics. Cathode rays, they can ionize air or gases. Cathode rays can penetrate through graphite layer or thin paper also. Cathode rays, they produce X-rays and heat when heating a heavy metal. Heavy metal, talking about metals like, heavy metals, uranium, polonium, okay, all those heavy metals, okay. So if they heat a heavy metal, then they produce X-rays, which are also called Roentgen rays. So these are some characteristics of cathode rays, and the properties you can have a look at a book on page number, say, 94. My book, old book, is 94, okay. Discovery of electron, article 2.1.2 of your textbooks for the detailed analysis or the detailed study of the property of cathode rays. Here I have summarized things to explain you in a better manner. Moving further, once the discovery of the cathode rays were done, now it was necessary for for those people, for J.J. Thomson and the other people at al, to get the charge of the electron. What are the charge carried by the electron? So this charge of an electron was, successfully, calculated and estimated and given to us by the experiment which was called a Millikan's oil drop experiment. Now in this experiment, by using an atomizer, oil drops were sprayed in the form of fine droplets in an apparatus like this, okay. Now these oil droplets, they entered this chamber, the first chamber, and then there was a small hole over here, pinhole, and this plate contains a pinhole which is connected to the positive terminal of a battery. Now the air droplets, this what do you call this oil droplets, fine, they just enter this pinhole and start moving in the downward direction because of the gravity, okay. Now now there is one more plate at the bottom of this chamber which is connected to the negative terminal of the battery. So there is an electric field over here, okay. The electrically charged, they are made of brass. Now X rays to produce charge on oil droplets, so X rays were allowed to pass from the other end, and then they entered the chamber and they hit the air, what you call oil droplets, to produce a charge. So by using this Millikan's oil drop experiment, whose detail you'll have to learn only when you pursue higher chemistry after class 12. But here, this much, what you call illustration of the Millikan's oil drop experiment is sufficient. So by this method, electrically charged oil droplets entered the electric field and were balanced between two plates by altering the field. So if you increase or decrease the field, the oil droplets were balanced between the two plates somewhere in the center, okay. And then their movement was controlled up and down. So by this movement, the charge of an electron was calculated, okay. Now Millikan found out that the charge of an electron was, single electron was 1.6 into 10 to the power of minus 19 coulombs. That C stands for coulomb, COULOMBS. That is the charge of an electron. So that is how the charge of an electron was determined. Now moving further to the mass of an electron. Now after the determination of the charge of an electron, the mass of an electron was given or calculated by the formula. The formula is given over here. Me is equal to the charge of an electron divided by charge by mass ratio, E by mass ratio. So by applying this formula, this value of E is already known and the E by M was determined, okay, 1.7588 to the 10 power of 11 coulomb per kg, and then upon simplification, the mass of an electron was calculated. So you must be able to do down this working. Similarly, the size of the electron was also calculated, because the energy of an electron is not a stationary particle, it is always moving. So the energy of an electron as given according to the formula was equal to E square by R, okay. If an electron is electromagnetic, then and it is moving also, so this relation becomes equal to the Einstein's equation, mc square. E square by R is more or less equal to mc square, or you can write R is equal to E square by mc square. So we know the charge E in ESU, electrostatic units, was found to be 4.774 10 power minus 10 ESU, and the mass we have calculated already over here, and speed of light is 3 10 power of 10 centimeter per second. So putting the values in the formula, R is equal to E square by mc square. After simplification, we get the value of the radius of an electron. It is very very small, 2.780 10 power of minus 15 meters. So I request you all to remember this working and remember this working over here, because this will be asked, okay, in the examination. Now, after the mass and the size of the electron were done, okay, moving further to discovery of proton. Protons were called canal rays, and this experimental setup and the performance was done by Goldstein, another fellow. Okay, so here in a discharge tube which is kept at a low pressure, okay, the anode is there, the cathode is there, but the cathode was a perforated cathode. It was a perforated cathode. So what happens from the perforated cathode? This chamber contains, you can call gas any gas is present in this, any gas particles. Okay, so from the cathode rays came out, they hit the gases, protons were generated. Okay, that is also possible. Otherwise, from the anode, when protons come out, they start moving in the direction of the cathode, perforated cathode. They pass through this perforated cathode and they cause a red glow behind the cathode. So that was how, a brief idea about how anode rays were produced. Now, looking at the properties of the cathode rays. Now, these cathode rays, they are the streams of positive ions of the gas enclosed in the discharge tube. The mass of each ion is nearly equal to the mass of the atom. This is a what do you call, a very good point over here. The canal rays or the protons are stream of positive ions of the gas enclosed in the discharge tube. The second point, they are deflected by electric and magnetic field. Definitely they are carrying charges, so they will get deflected by electric and magnetic field. The deflection is opposite to that of cathode rays because they are opposite in charge. They travel in straight lines. The velocity of canal rays is much smaller than the velocity of electrons because they have some mass and the mass is higher. They affect photographic plates also. They are going to affect photographic plates as well. Now, these rays can produce fluorescence on a screen. That means behind the cathode you saw a red glow over there. They ionize the gas through which they pass. So, if they are passing through a gaseous chamber, they will ionize the gases readily. Okay, now looking at the definition of proton. Protons, stable subatomic particle having a positive charge equal in magnitude to a unit of electron charge and a rest mass of, when it is at rest, it has a mass of 1.67262 in 10 power minus 27 kilograms. Otherwise, in grams it goes higher, which is 1836 times the mass of an electron. Now, when the number of protons in a nucleus equals the number of electrons orbiting the nucleus, the atom is electrically neutral. So that was a brief definition, simple definition of a proton. After that, after discovery of the protons, we come to radioactivity. Radioactivity over here. Now, radioactivity, it is a spontaneous degradation of nucleus and nucleus over here, nucleus. Okay, and please keep in mind, after proton there is one more particle in the nucleus which is not carrying any charge. So regarding the nucleus, I'll talk about after some time. So nucleus and transmission of one element to another with consequent emission of rays or particles. Those particles can be alpha particles, those particles can be beta particles. Okay, depending. Now, moving further, emission and detection of radioactive rays. This is a diagram which we have seen in class 10 also, where in a lead block chamber, a radioactive particle is placed, and as soon as it is and the chamber is opened, emissions start coming out. Okay, radiations come out. So alpha radiations, they come out, gamma radiation not deflected, beta radiation deflected. Okay, so that is how we demonstrate the emission and detection of radioactive rays on a screen over here. That is a photographic plate. Okay, now we can see there are two plates over here, negative plate over here and positive plate over here. The beta particles, they bend towards the positive plate and the alpha particles bend towards the negative plate. proving that alpha particles carrying positive charge and the beta rays carrying negative charge. But the gamma rays, they are not deflecting on either of the plates because they do not carry any charge. They are electromagnetic in nature. Now, moving further to the characteristics of alpha, beta, and gamma rays in detail, this chart becomes very important for all of us to see and understand. Alpha particle characteristics: two proton, two neutron. Beta particles, one electron, high kinetic energy. Gamma particles, it's a photon, light particle, electromagnetic, very high frequency electromagnetic radiation. Now changes from alpha particle uranium to plutonium. It changes uranium to plutonium. If an alpha particle is emitted from uranium, it becomes plutonium. Whereas when a beta particle is emitted from radium, it becomes polonium. But when a gamma particle is emitted, there is no change. Okay. Charges: alpha particle is plus 2, doubly charged helium nuclei plus 2, beta particle is minus 1, and gamma particle is 0. Mass of alpha particle relatively it is 4. It is 1 by 1850. It is gamma particles, no mass. Speed in kilometers per second. Just imagine, very high speed, 15,000 kilometers in 1 second. This is much higher, 3 into 10 power of 9 kilometers in 1 second. This is 3 lakhs kilometers in 1 second. Okay, so it is, you can see the relative speeds over here. Percentage speed of light, it is 5% of the speed of light. This is close to 100%, almost the speed of light. This is also almost the speed of light. Kinetic energy is 5 MeV, mega electron volts, 5 kV, 2 kilo electron volts to 1 mega electron volts, between 100 to less than 10 MeV. Okay, penetration power becomes important. Alpha particles, they have low penetration power. Large mass and charge can be stopped by a thin sheet of paper. We can use a paper to stop alpha particles. Also, beta particles, their penetrating power is slightly higher. It is moderate. Medium mass and charge can be stopped by a few millimeter thick metal. Gamma particles penetrating power is high. No mass, no charge, can be stopped only by a very thick cement or a steel block. So you can imagine over here the penetrating power of alpha, beta, and gamma particles. With the ionization power, something which can ionize, cause or produce ions, alpha particles, the ionizing power is very high because of the low speed, low penetrating power. Okay, so very high, large charge. It's moderate, low charge, low, no charge. Penetrating or ionizing power of gamma is absolutely negligible. So this chart is important for you all to learn it relatively with respect to the points your question will be asked from anywhere. Okay, now moving to one more chart, similar chart over here, which will make your idea very clear about this alpha, beta, and gamma particles, X-rays, and neutrons. Alpha particles symbol is He42, beta particles E0 minus 1, gamma particles is gamma 00, neutron is N00. Okay. Nature of radiation alpha particle is a helium nucleus of 2 protons and 2 neutrons. Beta particles high kinetic energy, electrons. Gamma particles high frequency electromagnetic radiation. Neutrons are they have very high frequency. Mass is 4, 1 by 1850, 0 and 0. Charge is plus 2 alpha particles, beta is minus 1, gamma and X-ray 0 charge, neutron is also 0. So this part, ionizing power, becomes very important for all these alpha particle, beta particle, gamma particles, gamma radiations and X-rays and neutrons. So better read through this properly. Read through this ionizing power properly for alpha, beta, gamma and neutrons. I'll just read this once more. Alpha particles, very high ionizing power, low penetration. Okay, very high ionizing power, very low penetration. Okay, then beta particles, moderate ionizing power, moderate penetration with a smaller mass and charge than the alpha particle. Gamma and X-rays, they have low ionizing power, highly penetrating, interact dominantly with the electron shell of the atom. Whereas neutron, they have the lowest ionizing power of the four, okay, amongst all these four. Very highly penetrating and interact primarily. Okay, now moving further to the next slide with respect to Rutherford's experiment and nuclear model of an atom, towards the discovery of the nuclear model by this fellow Rutherford. Here he performed an experiment, okay, where the source of alpha particles was used, and the alpha particles were allowed to converge or hit a thin gold foil. Okay, and then it was found that the particles after hitting the gold foil, they were scattered in different directions. It was found that most of the particles are undeflected. Okay, few particles are deflected. So based on this Rutherford's experiment, the nuclear model of an atom was estimated, after which we have some conclusions and observations made from the Rutherford's gold foil experiment, where from the radioactive source, when beam of alpha particles were allowed to fall in a deflector which is placed gold foil, it was found that most alpha particles travel through the foil undeflected, proving that the atom is mostly empty space. The second observation was some alpha particles are deflected by small angles, proving that the nucleus is positively charged, as is the alpha particle. And occasionally, an alpha particle travels back from the foil. Means only few of them, very less, negligible, one or two, they are bouncing back, which is proving that the nucleus carries most of the atom's mass, and nucleus is a very small, tiny space inside the atom. So these were the observations and conclusions which are drawn from the Rutherford's experiment towards the discovery of the nuclear model of an atom. Now, moving further to the much detailed conclusion from the alpha scattering experiment. The first one, the vast majority of the particles were not deflected at all, which means the atom must be mostly empty space. Okay, mostly empty space. The number two, some of the particles deflected through large angles. That means there must be a very small nucleus with a positive charge, because the particles are deflected, carrying positive charge. Alpha particles are also positive near to its surface. The number three, alpha particles repelled. Some of them repelled. Alpha particles are positively charged, so the nucleus must be positively charged in order to create an electrostatic force of repulsion. That means alpha particles are also positive, the nucleus is also positive. That's why there is a force which is called repulsive force. Number four, atoms are neutral overall. On the general, atoms are neutral because the number of electrons outside the nucleus is equal to the number of protons inside the nucleus. So that was the conclusion from the alpha scattering experiment, okay, performed. Moving to the next slide, we have over here now the discovery of neutrons after the discovery of the nuclear model of an atom. Now, discovery of neutron, it was carried out by the successful works of James Chadwick, where Chadwick observed that when a thin foil of beryllium, very very important, remember this, beryllium is bombarded with fast moving alpha particles, doubly charged helium nuclei. Beryllium changed into carbon, and a neutral particle having mass almost equal to the mass of proton was obtained. So, this is how neutron was discovered, okay, by a method which is like this experimental setup. Alpha particles are emitted, they were allowed to hit a beryllium foil or beryllium metal, and then the whatever is coming out, it was allowed to pass through paraffin wax, okay, to slow down neutrons, okay, and then it was observed on a screen. Protons detector come counter over here, how many protons are coming, okay. So you can see polonium, a radioactive element enclosed in lead chamber used for generation of alpha particles. So remember, polonium is used to generate alpha particles. Emission of non-ionizing radiation with very high penetrating power, and then neutrons displaces protons present in the wax, which are deflected and counted by the detector. So that is possible to count them also, okay. So by the help of this experiment, the neutrons were discovered by James Chadwick. So I request you all to learn this equation. Helium, that is doubly charged helium nuclei, which is an alpha particle hitting beryllium atom, and it is converting into carbon atom C612 and liberation of neutron, okay. So that is how the neutrons were discovered. You can have the lot of text from the book lot of literature from the book with regard to the discovery of neutrons by the experiment performed by James Chadwick. So, but I've summarized this very nicely so that whatever is important, only that much you have to remember from here. Okay. Now, moving to some characteristics of the subatomic particles or the fundamental particles in an atom. The electrons, negatively charged, mass of an electron is so much atomic mass unit, or 9.1 10 power minus 31 kg. If you look at the protons, characteristics of protons, the charge, it is positively charged. Okay. The charge of a proton is what? It is positively charged. It is what? It is positively charged. The charge of a proton is positively charged. Okay. Now, the mass of the proton is 1.0072766 AMU, or 1.6726. I want you to remember this value, into 10 power minus 27 kg. Remember this value for the electron mass. And regarding characteristics of neutron, it has no charge. It is neutral particle, subatomic particle. The mass is so much AMU, or remember this value. It is 1.6749, slightly higher than proton. Comparative mass neutron is 1842 times heavier than an electron. So this slide also becomes important for you all in this chapter, structure of atoms. So please go through this slide carefully, okay, with regard to the masses. Now, moving to our next slide, my dear boys, you have heard of these words atomic number and mass number. Okay, if you look at an unknown element X, that's a chemical symbol of an element which is unknown. Now, above this X, if I write any alphabet capital A, which is called mass number, it is called mass number. Above, superscript as a superscript, and this is subscript. The superscript is the mass number, which is obtained by adding the atomic number and the number of neutrons. Whereas atomic number is equal to number of protons or number of electrons. For example, if you look at carbon as an example, carbon as an element, an atom of carbon, its atomic number is 6, which means number of electron is 6, number of proton is also 6. But its mass number is 12, which means mass number is 12 means number of protons plus number of neutron, it is equal to 12 over here. Okay, so that is a brief idea about atomic number and mass number. Moving to our next slide, we have isotope and isobar, a very, very important concept to be remembered by all of you. Isotopes, as you have learned in class 9, I remember, they have same atomic number, but their mass number is different. But isobars, they have different atomic number, but they have same mass number. In isotope, number of proton is same, but in isobar, number of proton is different. Isotopes occur at same place in the periodic table, but isobars, they occupy different position in the periodic table. Example of isotope is given to chlorine isotopes, Cl1735, Cl1737. Whereas isobar example, germanium and selenium, the mass number is same, atomic number is different. Better example, you can have a look over here, carbon 12, carbon 13, carbon 14. And over here, example of isotopes of lithium, lithium 3, 6, 7, 8. And over here, example of isobar, very good example of isobar. Remember this. This will be coming in your objective question answers. Argon, potassium, calcium, they are example of isobars because their mass number is same, atomic number is different. Okay, so that was the concept about isotope and isobar. Now, moving further to the next slide. If you look at the next slide over here, nature of electromagnetic radiation and atomic spectra. Okay, now have a look very carefully at this diagram. The electromagnetic spectrum, wavelength in meters, this way, wavelength in meters. Now, beyond gamma rays, they are cosmic rays, cosmic rays. Now that I'll come later on. If you look at the left hand side, radio waves, they have the size of buildings. Microwaves in meters, between 1 to 10 power minus 3 meters, they have the size of grains of sugar. You know what is sugar? You add in tea to prepare tea, to make it sweet. So size of sugar grains, microwave. Infrared radiations, they are size of protozoans, protozoans bigger than bacteria. And visible spectrum, visible light, bacteria. Ultraviolet light, size of molecules. X-rays, atomic size. Gamma rays, atomic nuclei. So this is a comparative analysis and comparative study, brief idea about the wavelength in meters about the different types of electromagnetic waves: radio, micro, infrared, visible, ultraviolet, X-ray, and gamma rays. Okay, and you can just compare and get an idea from over here regarding the wavelengths. Okay, in meters. Now, moving to our next slide, we look at a theory which is called light wave theory. Okay, since light behaves as a wave and is made of both electric and magnetic fields. Remember that it is made of both electric and magnetic fields. It is categorized as the electromagnetic wave in most of the cases. Electromagnetic fields oscillate perpendicularly. Electromagnetic fields, they oscillate perpendicularly. If the magnetic field is this way, electromagnetic field oscillate this way. This way, they will oscillate this way. Are you getting it? If the magnetic field is this way, the electromagnetic field oscillate this way. Okay, now here you must remember electromagnetic fields oscillate perpendicularly to the direction in which the wave travel and are also perpendicular to each other. Hence, they are known as transverse wave. So please remember, these electromagnetic waves, they are transverse. They are transverse waves. Following are some significant characteristics of light. Transverse means waves like this, waves moving in this direction, this way. This transverse wave. Okay. Now, light has a definite speed. That is, the speed of light can never change on its own. A single beam of light can travel the earth around 7.5 times in 1 second. Just imagine. We know, okay, like almost all other electromagnetic waves, light waves travel with the speed of 3 in 10 power of 8 meter per second or 3 in 10 power of 10 centimeter per second. A light year is the distance that light waves travel in 1 year. To deal with light waves, we need to consider a sine waveform. We need to consider a graph, a sine waveform, okay, a graphical waveform. That I will discuss after some time. Now, brightness, or we can say the intensity of light, is represented by amplitude and depends on the distance and how much light the source produces. The light emitted from a source is measured in lumens. The wavelength of light waves is shorter than infrared waves. Remember that. After that, as per the formula devised by Planck, the energy of a photon is directly proportional to the frequency of light, and it is given by this formula: E is equal to hf, where h is the Planck's constant. Okay, 6.63 10 power minus 34 joules second. Okay, so this was a brief idea about the light wave theory. Now, this light wave theory, you can have a look at it from the textbooks. I have simplified this light wave theory for all of you, so you can have a look at page number over there. Page number 103 in my textbook, where it is written as nature of light. Number B, wave theory. There are 5 points given, and after that, wave motion and its characteristics has been discussed very properly. Okay. Now, moving to our next slide regarding this wave motion and its characteristics. Look at the two diagrams over here. The first diagram first. Okay. Now, this red arrow, that is an amplitude. This is a wave. This is a wave. This is a wave. Okay. This height, it is called the crest. This is called the trough. The distance between one crest and another crest becomes the wavelength. Okay. And direction of propagation of the wave, it is in this direction, and they are transverse wave. Okay. So that's why this arrow is given over there. The waves direction of propagation of the wave in this direction. Now, if you look at the other diagram over here, so these are some impressions drawn over here to make us understand the wavelength from here to here. One wavelength, this is the amplitude, okay, and then we'll discuss about the frequencies. Now, just let me finish off this portion for a while. Characteristics of wave motion. Okay, wave motion is nothing but it is a disturbance produced in the medium by the repeated vibrations, periodic motion of the particles of the medium. There is a regular phase change between the various particles of the medium, going up and coming down. Each particle starts vibrating a little later than the particle just ahead of it. Then number three, the velocity of the wave is different from the velocity with which the particles of the medium are vibrating. So this point becomes important. That means the velocity of the wave is different, and the velocity of the particle is also different. Okay, so the velocity of the wave is different from the velocity with which the particles of the medium are vibrating. So these are some important characteristics of wave motion. So now I would like to stop my class over here only, because in the next class I'll be explaining you in detail regarding the wave motion and its characteristics by talking about the different wave parameters which is there in your syllabus. Okay, so please hang on, please do not leave the class. Let me capture your attendance digitally and then you may leave the class after that. Okay, please hang on. Okay, I have recorded the attendance. Okay, you may leave the class or get ready for the next class. Thank you so much. Have a nice day.